So, does that mean it was super easy? Well, let's see. Real quick, with a raise of hand, how many of you guys used or tried to use the formula? F inverse prime of B is equal to F inverse prime of B is equal to F prime of A. Good. How many of you guys tried implicit? Okay, a couple. Let's go ahead and see how we did. So, the opener for today, practicing skill from yesterday. Before we grade homework, P.S., get a colored pen out and ready. Let me get rid of this. I'll probably try to do it both ways just to show what's going on. But let's go ahead and go the first way. So the first way, let me go ahead and just label formula. The colored pen is for when we go to grade in just a second, in case some of you guys are stressing. Don't stress. We know F inverse prime of A is equal to 1 over F prime of not A, which is why we call the A B. So we say F inverse. It would have the point 2 comma whatever, which means whatever comma 2. What gets plugged in here? Do we know what that is yet? No. So what do we need to find? Yeah, we need to find the x whenever y is equal to 2. Did you guys go there? That's just to figure out what number to plug in this spot. Huh? What are we supposed to do? Trial and error. I heard someone say error, and I think you meant trial and error. Right? The hint in the card. Yeah, guess and check. Trial and error. What did you guys plug in first? Nice! Because what's 0 cubed?
0.
Plus, what's 2 times e to the 0? Ah! So what's x equal?
0.
Because we did math and figured it out? No, because we guessed and checked. And it was so much faster, right? And it was possible. How else do you solve this? Factoring? Calculator? It won't be a calculator question. Okay, good. Whew, we figured it out. The spot. What was the point? 0 goes in. Ah! That spot. So we're done. Who's F prime? Oh, that's right. Now, maybe you might want to do F prime up here in like the introductory work. Maybe you would want to do F prime up here in the introductory work. This is a pretty easy F prime, though, so I'm going to go ahead and just do it right in the formula itself. What is F prime? 3? Something squared. You guys know why I'm leaving it blank, right? Okay. Plus, what's the derivative of 2e to the x? 2e to the, So who's my x? Who am I plugging in? Got it. So I'm plugging in 0 there. Different color just to show. I'm plugging in 0. I'm plugging in 0. Oh, we already know what that is. Because that's just going to be 0, kind of like it was a second ago. And then e to the 0 is 1. So therefore, the final answer is just 1/2. The final answer meaning F inverse prime of 2. Dun, 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 dun. Who got there before me? Give me a thumbs up. Okay. A few of you guys got a little lost, a little stuck. I know a couple of you guys did it implicitly, so let me really quickly go through how it would look implicitly, and maybe you guys can see how it's the exact same math that's required, just coming from a different direction. This way is getting to the derivative of the inverse using the original the whole time. Implicit says, let's actually think about let's actually find the inverse. So implicit says, let's take that original and let's go ahead and switch to x and y. X and y, you have a representation of the inverse. You have a representation. So instead of sticking with the original the whole time, we actually go to the inverse. And we say, we need the inverse's derivative. And I think that's where homework started. It actually had you finding inverses, like solving for y equals for f inverse of x. If you have the inverse, you can just take its derivative. But why was this formula nice over here? Can we get y by itself? So getting the inverse as an f inverse of x equals is impossible. We can't get y by itself. We can still derive it, but we can't derive it nicely with like y equals, all nice and isolated. So we're going to have to do implicit. And implicit's going to give us 3y squared plus 2e to the y. Wait, what am I missing for both of these since they all have y's? They both would have a dy dx. So I'm just shortcutting a little bit. dy dx, aka d dx of f inverse, that's what's going on right down here, is equal to 1 over 3y squared plus 2e to the y. Well, wait, what do I plug in? I'm trying to find f inverse prime of 2. Wait, when we talked about the inverse a second ago, what point was there to an inverse? What was the inverse's x? What's the inverse's y? Oh, that's what's supposed to get plugged in. The y of the inverse is supposed to go in the y spot. But guys, who is the y of the inverse? It's the same thing as the x. So when you use the formula, it's saying take the x from the original. And if you're going implicitly, it's saying take the y of the inverse. But what's true? They're both the same thing. And how do you find them both? The exact same way. So if you had gotten here and been like, I don't know how to find y, what you would have needed to do was come back here and say, well, who's my inverse? Oh, there he is. X is 2. So you would say, in order to solve for the y, okay, x is 2. Do you see how it's the exact same equation with an unknown in the exact same spots? It's the same exact thing. So when you solve, it looks a little different because you're dealing with the inverse this time, so it's going to be a y instead. But it's the exact same work you were doing back here when you needed an x of the original to plug into the original's derivative. So then we come back here and we say, okay, it's time to plug in. And when we plug in, we get 3 times who squared plus 2 times e to the who, still 0. And so we still end up with 1/2, being f inverse prime of 2. So the formula says, I don't ever actually need to make a representation or solve for the inverse. I can use the original the whole time. Implicit, or if you actually solve for the inverse function and you go from there, it says take the derivative. He's the inverse. Okay, take the derivative. He's the inverse. But you need to use the inverse's point in order to plug in. But it ends up being the exact same math, the exact same answer. And with that, we get to, well, we'll get there in a second. Homework number 13, 2.6a. Let's grade. I think I have the book open. That's not that tab, that's this tab. Yeah, 2.6, I have the book open. As you guys turn and get ready to grade the evens, I think homework started off in section number, well, the first section, asking you to verify f as an inverse, aka switch x and y, solve for y. As long as there's not a plus or minus, that guy was invertible and he has an inverse function. And if you were able to get f inverse of x written, you could have just taken the derivative and then plugged in the a. But the nice thing is, number one, and they knew this was a tricky section. They said, go check out the example to see what we want. And then the very first one was pink, which meant go check out the QR code, the video, and see what they want. To figure out what they were looking for in section 1. Just wanted to point you guys to the fact that I very, very, very carefully chose a book that gives you resources to hopefully know how to tackle at least what the objective is and what the general gist is of what they want you to do for each and every problem, even if we haven't done one exactly like it in class. So number 2, why did I give you number 2 and not number 1? Well, I was hoping I did give you number 1, never mind. Why did I give you number 2 after number 1? What was I hoping if you needed it you would do? Watch the video or go back to the example or both. So number 2, when you switch x and y and solve for y, did they not actually find the inverse function? Oh, they didn't. Little stinkers. If you switched x and y and solved for y, you definitely would have found a cubed root function. So yes, this does have an inverse. They actually ended up just using the formula the whole time, but they didn't have to. So I'm going to have you guys check the final answer of negative 1/6. I'm going to quickly show you there was another way of solving. I don't just mean implicit. Didn't they have you switch x and y and solve for y? So x minus 5 divided by a negative would be 5 minus x, and then cube rooted. Someone double check me. Does it look like the cubed root of 5 minus x? Is that right? Anybody who found the inverse? This is a function, so I could say f inverse of x is equal to the cubed root of 5 minus x. If they wanted you to find f inverse prime of, don't you have the inverse? Oh, sorry, what's wrong? A 2? Oh, thank you. I didn't write it there, huh? Okay, so go ahead and subtract the 5, switch the signs, and divide by 2. Ugh. Yeah, but I switched the signs. The negative switched my signs from a x minus 5 to a 5 minus x. So I could make that, I could technically pull that out. That's kind of nasty, though. I could pull out like a 1 over cubed root of 2. Ugh. That's just going to be a constant. Guys, I have the inverse, so I can just take his derivative and plug in 7. So technically, you could have used the formula coming back here. F inverse prime of a, well, of 7, which we call a b, right, is equal to 1 over f prime of a. We could have done that. Or we could have actually, after we found the inverse, get y by itself, we could have just taken the derivative. And so the derivative of the inverse would have been 1 over the cubed root of 2 times, would have brought down a 1/3. We would have ended up with this guy to the negative 2/3, which would have been times 1 over 5 minus x to the 2/3 times u prime, which was a negative 1. Oh, that's disgusting. Yeah, it's not very pretty. We would have gone ahead and then plugged in 7. 5 minus 7 is a negative 2, and negative 2 squared actually ends up being a positive. So you would end up with negative 1 over 3 times. And at the end of the day, you'll have the root of a positive 2 cubed, which ends up canceling and equaling negative 1/6. But to be honest, what looks kind of simpler just from you guys looking at the work? This or that? Yeah, so maybe even if it is possible to get y by itself, sometimes when you find an inverse function, it's a lot messier than it was to begin with. Maybe it's sometimes nice just to go with the original function and say, hey, what's f prime? There he is. Okay, I need 1 over f prime, negative 6 times somebody squared. But remember, if I'm trying to find f inverse prime of b, what are we supposed to be plugging in? A. So I need to go ahead and think about, okay, my f inverse has an x of 7, which means my f, whose guy I need, what did they do to solve? They didn't even show it, the little stinkers. Well, what did you do to solve? Set y equal to 7. And if you guys notice, this was actually a really nice one, because can't you solve for 7 by subtracting the 5, dividing by the negative 2, and cube rooting? And you guys end up with x equals negative 1. Ha-ha. Dun, 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 dun. And I didn't need any of that. Both ways work if you can get y by itself. Both ways work if you can get y by itself. But this way did look easier. Ryan, what's up, bud?
So nicely all when it's easy to plug in and just find the other variable.
Meaning like how I got x nicely?
Yeah.
Uh-huh. But what was the opener that we did, Ryan? Was it nice and easy to do this one? It was well, no, technically it was impossible to solve by hand, which is why we had to resort to what? No, it's okay. It was impossible to solve by hand, meaning to actually get x alone. That's impossible, which makes it really discouraging unless you remember the hint or the note that we put on the forever card, which says, when it gets difficult or impossible, what do we try? What do we resort to? Plug what in? Start at 0. It doesn't work. Try 1. Doesn't work. Try 2. Doesn't work. Try negative 1. Try negative 2. It should work, at least for the AP guys. In homework, though, we're going to see if there's something that was actually impossible where you needed to get a decimal. Because it's possible in our book They might have assumed that you were using your calculator on some of these, so maybe it got harder. So let's check it out, Ryan, okay? Number 8, we end up with -2. Which, to be honest, does end up being a fairly nice one also. When you set y equal to 2, you could multiply up, distribute, combine like terms. You get -2. They went into why it passed the horizontal line test and has an inverse. That's good background information, but yada, yada, yada. Number 10, also pretty nice as far as solving. So far, the beginning of homework was pretty nice as far as setting equal to 2. You can square both sides. You end up plugging in 8, and you end up with 1 over 1/4, which is just 4. Number 12. Number 12, they went ahead and actually found the inverse and then took the derivative, but you could have also used your formula as well. This one got a little bit tricky if you didn't realize that this point they gave you was not an inverse point, this was an original point. So you could have either plugged in the x of the inverse, the x of the original, you could have either plugged in the a and then done 1 over that, or you could have gone implicitly and plugged in the b. I apologize, there's the b. With the b of -1. Well, did they ask you to do it implicitly and with the formula? What were the directions on number 12? Oh, that's it? Oh, okay, so I'm going way deeper than it asked you to do. I apologize. The final answer for the derivative of the inverse is just -1/4. I apologize. Number 20. How many of you guys, just real quick, because a lot of you are using the formula, how many of you guys got a little confused on number 20? Okay. Okay, that's what I was afraid of. Once you get really good at the formula, it starts to get confusing just doing it the old-fashioned way. Because the old-fashioned way is what you would have done before you ever learned about inverse functions. You would have just taken this guy and been like, whatever, implicit differentiation. I don't want to get y alone, forget that. Take the derivative. Okay, cool, derivative is 1. Derivative is 2 times 1 over u times u prime. And there's a dy dx at the end. You could have moved everything to one side and gotten the dy dx. And then they actually gave you a point. Now here's where it was a little crazy. Since they gave you the inverse to begin with, since this is the inverse, guess what? That's the inverse's point. What do you need from the inverse's point to plug in? You're with the inverse. You're not using the original. Are you using your forever card? No. So plug in what they ask for. What do they ask for? So plug in y. So plug in 2. So where it gets a little tricky, if they already give you the inverse, which is not really tricky. If you hadn't done this section, you wouldn't be confused about how sometimes things switch. But that's only when you're working with the original the whole time. We have the inverse. We derive the inverse. We plug in, okay, fine, whatever. Plug in the y of the inverse. Dun, 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 1/8. This is a good old-fashioned implicit problem. If you wanted to use the formula, you would have had to go back, ironically, gone back to the original. If you wanted to use the formula, you could have gone back to the original, but you would have had to switch your point and say, and f's point is 2, 0. You would have had to not only switch the point, but also switch the point itself. Then you could have done, hey, f inverse prime of 0, the x of the inverse, is equal to 1 over f prime, 1 over u times u prime. It would have been the exact same work, just now we would have been plugging in the x, which is still 2. And it ended up with 1/8 also. So if you wanted the formula, you actually would have had to switch the point and the function to be able to use it. So in this one, since it was written implicitly, you just want to go implicitly. Don't even think about the formula card. Don't even think about switching anything weird. And then the last one, I think, was number 72. And this one really made you dig into the concept. If you know the slope of the tangent line, aka the derivative to f at this, you can know inverse at that point, AB becomes BA. We know that. But the slope is not parallel. The slope is going to be 1 over, just like our formula card says. Just like our formula card says. And then in letter B, if we know the slope of the tangent line or the derivative, we can switch it and say the slope of the inverse at 1, 2 is 1 over. So with that, kiddos, we're going to go do homework questions, but I want you guys to grab out your calculators real fast to further cement this just a little bit. In our notes, didn't we write down a cubic function and we kind of just didn't ever go back to it? Had to do with differentiability. Okay, I want you guys in your notes. We're coming back. Don't worry, I'll go over homework questions. I'm not just leaving you high and dry. But we're coming back to this page real fast because this page has to do with this one right here. What I want to show you on this page is what that very last question in homework was trying to make you deal with. Number 72, was that it? Okay. I want you guys to go ahead and put x cubed in your calculator as y1 and a cubed root of x as y2. I want you to go ahead and put x cubed as y1 and a cubed root of x as y2. What's the relationship between these functions, guys? They're inverses of each other. Good. I want you guys to go ahead and go to their graph. I want you to be in Zoom Standard, please. Oop, I'm definitely not. Lo siento. Zoom Standard. There we go. And I want you guys to find for me derivative of, and I think I'm going to have to go a little bit higher on this graph set. So hold on. Pause. Do you know how to use your calculator in the graphing menu to find a derivative? Does anybody know how to do that? Okay, take a second. I want you to look under, where do we always do everything in the graph? Our maxes, our mins, our intersections, our zeros. What menu is that? Second trace. Go in that menu, second trace, and I want you to see if anything looks like a derivative. Yeah. dy dx. Peek real quick in your group. Does anybody not have a calculator? If they don't, help them out, help them out. If they don't, help them out, help them out. I want you guys to try to find for me, using your calculator, the slope at 2 of y1. I want you to find the slope at 2 of y1. So what is f prime of 2? When you guys do the dy dx, it should ask you for an x equals. I want you to plug in 2, and I want you to look at the y1 graph, aka the x cubed graph. What do you get? Yep. Yeah, your calculator sadly does like an estimation of derivatives. It is 12 perfectly. Wait, how should we know that it's without even using our calculator? It's not 0.00. What happened? 12. Oh, it's 12 perfectly. Calculator was a little off with the 0.000 weirdness. Now I want you to go ahead and find from the derivative of dy dx of the other function, aka the cubed root function at 8. 8? What? Why are we doing it 8? I want you to find for me the dy dx at 8 of the cubed root function. So what's f inverse prime of 8? You guys are reading off a funny fraction, right? Okay. Couldn't we also figure out what that funny fraction or what that funny decimal is by taking a derivative? The derivative would be 1/3, right? Bring down the 1/3, and then x to the negative 2/3, which would be 1 over the cubed root of x squared. I'm plugging in 8. The cubed root of 8 is 2. 2 squared is 4. 4 times 3 is 12. Can you guys check in your calculator, is 1/12 the decimal that you saw with your dy dx? Is 1/12 the decimal that you saw with your dy dx? What's another way I should have been able to do that without doing all the messy power rule stuff? Why did this guy have to be 1/12? What's this point? 2, plug it in, plug it in. What's it going to correspond to on the inverse? 8/2. And how does my formula card say slopes of originals and inverses when they correspond across that y equals x reflection? What's the relationship between their slopes? F inverse prime is going to be 1 over, right? F inverse prime of B is equal to 1 over F prime of A. Why does it make sense they're not the exact same? Hey guys, how steep is this dude? How steep is that? Super steep. It's almost like it looks almost vertical. I mean, it's not. It has a long way to go until it gets to infinity, but it's still super steep. How steep is this guy? Not that steep. Is it still positive? Yeah, it's still positive. Is it going up very fast? No. If there are reflections across the y equals x lines, slopes cannot be the same. That doesn't work, but 1 over makes a lot of sense. As far as what this guy is doing going up and then over, this guy is doing but going over and then down. Or I should be going over and then up, just it's barely there. Okay? This is what number 7. You guys seeing how corresponding points are not the same point, because what this guy is over here is going to be flipped and over across the y equals x line over there. Their slopes aren't going to be the exact same, but they're related, and they'll always be related the same way. Whatever he is, he'll be 1 over their reciprocal. So in this little note that I put into your guys' things that we never actually talked about, the HTLs of f of x become the VTLs of f inverse of x. What am I saying? What's an HTL? Horizontal tangent line, aka when f prime of x equals 0, what's going to happen to my poor little f inverse? What's the relationship of slopes when they correspond? I'm going to put B. So when f prime of A equals 0, then what's going to be f inverse prime of B? AKA? So the horizontal tangents are going to be the vertical tangents. The horizontal at 0 tangents are going to be the vertical tangents of the inverse. That's just a quick little application. Let's go back to homework real fast, because I know we went over the actual answers to homework, but we didn't go over questions. I can't promise I can work out everything, but I can do 1 or 2. I think 1 or 2. As you guys are telling me what your questions are and I get ready, let's not distract you. Let's not distract you. Sorry, I was going to have you multitask, and that's a bad idea. Is there, well, let's pause. Let's pause. Let's not go over even questions, because you just, some of you need to go back to the YouTube video from today and maybe mull over the answer key. That's always an option to you for evens, the same way you mull over, hopefully not just copy and cheat from CalcCAB video. You can mull over the evens. Do you have any odds that you knew what the answer was, you tried CalcCAB and got stuck? Okay, 5. Anything else? Okay, think about it just a little bit. Ask one more time. Number 5, aha, he's trig. And actually, Ruth, he's a perfect introduction for today. Guys, what's the title for today? Inverse trig. Number 5 was asking for us to find f inverse prime of A. What did I want you guys to change with A? Let, oh, I didn't do the right color. You guys know the idea though, right? Because I want you guys, whenever it's an inverse, to be thinking of that guy. But either way, no big deal. We got this. Okay. So if you just use the formula, we could say f inverse of 1 over. Now, some of you might have been realizing taking f prime, derivative of sine is cosine, might be helpful before you get to the formula. But what else is helpful before you get to the formula? Thinking about who you have. 1/2 is an x of the inverse, which means, what is it of the original? So what did you have to do? Find him. How do we find him? Set 1/2 equal to sign. The y needs to go in the y spot. Then we have to think of unit circle. In between negative pi over 2, negative 90, and pi over 2, positive 90. Where is sign positive? Well, none of that quadrant. Forget him. Sign's negative. And sign is the y value. He's going to be the little positive 1/2 at pi over 6. Had to go back to the unit circle and think, when is my y 1/2? So we can go ahead and say, oh, hey, pi over 6 is my answer. Pi over 6 is my x. Pi over 6, if you want to think about it, is your a. So then we go ahead and say, what's f prime? Oh, that's right, cosine. Where is it at? Pi over 6. Oh, hey, this was the example we did yesterday in class, but maybe you didn't exactly know how we did it. There we go, cool kids. Possible to use the derivative of an inverse formula for finding the derivative of sine inverse at 1/2. Yeah. But wouldn't it be nice if maybe there were some formulas about how to deal with trig without going through this every single time? I wonder if that's a thing. And the answer is, why isn't it going forwards? There we go. The answer is yes. The answer is yes. Now, here's the dealio. The beginning of notes, I started off with saying, hey, remember sine, cosine, tangent, cosecant, secant, cotangent? They were things. Do we have graphs of those things on our forever cards? Yes or no? So I don't want us to worry about the original functions of sine, cosine, tangent, cosecant, secant, cotangent right now, because you already have them on your forever cards. What I want you to realize is what happens when we take the inverses of them. What happens when we take the inverses of them? So even though I have all the old graphs on here, I don't want you to write them all down because you have them in your forever cards. You don't need them. I'm going to take them all away. And instead we're going to talk about what happens when it's sine inverse, cosine inverse, tangent inverse, cosecant inverse, secant inverse, and cotangent inverse. Now, if we were to flip the entire sine curve, it's not invertible. It does not pass the horizontal line test. We would have some major issues. But we do this thing called keeping it invertible, restricting the domain to make it pass the horizontal line test, all review stuff from last year. And we actually just end up with this little piece for sine inverse. That's the invertible piece. And the invertible piece has a domain, has a left, has a right, of, I apologize, it should be level. It should be like this. There we go. That's flipping the sine curve. The domain is going to be from -1 to 1, and the range is going to be from negative pi over 2 to pi over 2. The x's and the y's switch. The x's and the y's switch. Cosine, he's a funny dude. He starts here and goes down. So actually he's going to have something that looks kind of similar. But it's going to be for a different domain and range. His domain is still -1 to 1 because his y's still only go from -1 to 1 to begin with. His range, though, is going to be 0 to pi. Tangent inverse. We actually have him on our basic graphs. He's a one tangent that's been flipped, and his domain is -infinity to left, forever, right. But his range is negative pi over 2 to pi over 2. Open intervals because he has vertical asymptotes. Well, he had vertical asymptotes. Now he has horizontal asymptotes. Cosecant, ugh, that's gross. He's the guy that bounces off of sine. He's the guy that bounces off of sine. And when he bounces off of sine, we actually end up taking his two branches and reflecting them. He would end up looking like, okay, this is nasty, like this. this. There we go. And then like this. Bless you, bless you. I want to make sure I'm flipping him right. Sine. Oh, no. Sorry, that's secant. My bad. My bad, my bad. I flipped him off with cosine. Secant looks like that. Cosecant flips off of sine. And that looks like... Oh, sorry, the visual on this is hard. Skimming... No. Skimming... Forgot there's a gap in between. There we go. I didn't give him a gap in between. There we go. Long story short, his domain is going to be negative infinity to negative 1, and then 1 to infinity. It's the flip of the range of cosecant. And then his range is going to be negative pi over 2 to 0, and then 0 to pi over 2. This guy's also going to be negative infinity to negative 1, 1 to infinity, where there's a vertical asymptote, pi over 2 to pi. If you guys notice, oops, that's a closed. It looks like cosine for secant, and that is from 0 to pi still. There's just a split up at pi over 2, because that would be a 0 of cosine inverse. So when you flip it, we'd have some issues. Same thing down here with cosecant. Cotangent inverse is that guy flipped. That guy flipped ends up being, instead of straddling the axis, there we go. Domain is still negative infinity to infinity, but he's from 0 to pi. Nope, he has vertical asymptotes there. Now some of you are going to be relieved to say, or to hear, that you don't have to memorize all this. The only graph that's actually important for you to keep in mind is this guy, the only graph, and he's already in our basic graphs. What is important is knowing what's allowed to come out, knowing what the ranges are. And it's not always important, but sometimes you're going to have to be actually finding inverse sine or cosine or tangent of things. Sometimes you're going to have to be finding inverse sine, cosine, tangent of things, and you're going to need to know what angles you're allowed to be looking at. Like the one that Ruth brought up, you're only allowed to be looking at negative pi over 2 to pi over 2 because the inverse of only spits out answers in between there. They told you that time, but other times you're going to need to know which ones to pull out. So the reason I gave you all of this was so that you had what answers are legal to come out of a sine inverse, to come out of a cosine inverse, to come out of a tangent inverse, etc., etc., etc. But that was just saying what kinds of answers, when you plug into inverse trig, are you allowed to get out? That's actually pre-cal. That's actually pre-cal. Getting ready for the calculus questions, we just have to remember real quick. Hey, an original function, a sine function, remember what goes in is going to be an angle. What comes out is going to be a ratio. So for sine, that ratio is opposite over hypotenuse specifically, right? SOHCAHTOA. But for inverse trig, remember what goes in are the ratios, aka the opposites over hypotenuses. And what comes out is going to be the angle. Technically, even though you might be given an f of x in context of what we showed, the f of x is the original, this would be the inverse. The inverse function of sine is sine inverse or arcsine. They mean the same thing for our purposes. But when you're given a sine, cosine, tangent value or a ratio of sides, for inverse trig, when you're given a ratio of sides, you're going to be figuring out the angles, which means you need to know your unit circle backwards and forwards. we saw last year also. You need to know your unit circle forwards and backwards. I give you an angle, you give me a ratio. I give you a ratio, you give me an angle, but only in these blue starred intervals. Now, we're not going to necessarily right now go review pre-cal, so I'm taking that out. But I am going to show you where one of these formulas comes from. Now, guys, this homework isn't due tomorrow. There's no way. But it almost could be due tomorrow, and I want to show you how, because some of you guys are coming to zero period in the morning, or you might have more time tonight than tomorrow night. I'm going to go more into the ideas tomorrow as to where the formulas come from, but you guys have learned when there are derivative formulas, you just have to learn how to use them. So there are 6 derivative formulas for sine inverse, cosine inverse, tangent inverse, cotangent inverse, secant inverse, cosecant inverse. They are in your book. I will write them down when the bell rings. They'll be saved in the notes and they'll be on the YouTube video. You could write this down, make a forever card out of it, and start playing with it tonight. You don't need the preview stuff to be able to do it. But let me show you what the preview stuff is. We could take this guy, kind of like that implicit one that we saw in homework, and we could rearrange it to make it something where we could use the formula. If you didn't know the formula, the only way to do this is using the original, which we would have to go this way. Using the pre-cal stuff that we just talked about, I could say that x over 1 is equal to an opposite side over a hypotenuse side, and y is equal to an angle. So I could actually come over to a triangle and say, hey, it's a triangle with an angle y, an opposite of x, a hypotenuse of 1, and with a little bit of Pythagorean, I could do c squared minus b squared is a squared for the third side. I could come over here and I could take the derivative of both sides, saying, you want this guy's derivative? Fine, I'll find it for you. I could get 1 equals cosine of y times dy dx, which ends up equaling dy dx is equal to 1 over cosine of y. And I could say, well, that's great and all, but these formulas aren't going to have y's in them, they're going to have x's in them. Well, how am I supposed to? We could come over here and say, wait, isn't cosine of y, just looking at the triangle, adjacent over hypotenuse? We could actually go and plug it in and say, you know what? If we just memorized it, guess what's going to happen every time we try to take the derivative of an inverse sine? We're always going to get this. And as I promised, when the bell rings, I'm going to come over here and finish filling in the rules. Squared times except who was that the derivative of? I'm dumb. Down the other 5, you guys can check on it tonight and even start playing with the derivatives, because literally it's just using 6 new rules. Bye guys, I'll see you later. What's wrong? Why are you so disorganized, buddy? Oh. Yeah, so it's messing you up a little bit. Hang in there. Bye. Hey, Robbie.